Okay, so this is an explanation of the pressure graph that's associated with the cardiac cycle. And we're going to map that alongside then the changes in the heart itself using the simple box diagram. And we've obviously already set up and established this sequence here, that contractions and relaxations of the chambers of the heart change the volumes of the chambers of the heart. And this changes their pressure and causes pressure differences between the chambers or between the chambers and the arteries. And this can open and close valves and allow blood to flow. Okay, so we're going to start this time with atrial systole. Okay, so this is then the contraction of the atria. So we'll make that change on our diagram. So there's the contraction of the atria. That's decreased the volume of the atria and has increased the pressure. I'll use my red pen here for pressure and the blood flow. And it's increased the pressure then above that of the ventricle. So the ventricle has a lower pressure. So the difference in pressure is that the atrial pressure is greater than the ventricular pressure. And so the bicuspid and tricuspid, the atrioventricular valves open, allowing blood to flow into the ventricles. Okay, or force the remaining blood into the ventricles. So what does that look like on our graph here? Well, I've got a scale on the side here of my y-axis of the blood pressure, which can be measured in kilopascals or in millimeters of mercury. Got time along the bottom here. I'm going to show one cardiac cycle. So that's 0.8 seconds in the scale there. And I'm going to use three colors then to represent the different pressures. The left atrial pressure in green, left ventricular pressure in red, and aortic pressure in blue. So we've already established that the atrial systole is the contraction of the atria, and so the pressure in the atria increases during that time. And as blood leaves, the pressure decreases slightly. And ventricular pressure then is lower than, but actually is going to track the pressure of the atria. So it's just lower than, which means the valve stays open. And the reason why it's going to track then the pressure is because with the valve open, as it was from diastole, essentially the atria and the ventricles are acting as one chamber. So a contraction in the atria is going to have an effect on the pressure in both chambers, but it will be greater effect in the atria because that's closer to the contraction. So that's atrial systole. We're now going to then move on to ventricular systole. Okay, so in ventricular systole then, again using our sequence, the ventricles contract and the atria relax. So we'll show this. So atria are going to relax back to their original volume. Ventricles are going to contract. So the ventricular volume has decreased, the atrial volume has increased, and so the pressure now is greater in the ventricles than it is in the atria. Okay. And that means then that the bicuspid and tricuspid, the atrioventricular valves, are going to close because they're one way. So the pressure difference now in the opposite direction means that it's going to close those valves. Like so. So blood can't return back to the atria. So let's have a look on our graph then of what that does. So the atria have relaxed, okay, and the ventricles have contracted. So the ventricles are now, ventricular pressure is going to rapidly increase, okay, because the ventricles are now contracting. And the atrial pressure then is then lower than this. I'm just going to extend that line very slightly. So what we've got here then is the first point at which these lines cross, okay, and it's the ventricular pressure that's crossing the atrial pressure, so it's becoming greater than the atrial pressure. So this crossing point and the increase of the ventricular pressure then represents, in this case, because it's the left side of the heart, is going to be the bicuspid closing. Okay. Now, within ventricular systole, we also need to then compare not just the ventricles in the atria, but the ventricles and the arteries at the top of the heart as well. So we'll go through that again. The ventricles have contracted, the volume of the ventricles has decreased, the pressure is now greater in the ventricles than in the arteries, the pulmonary artery and the aorta, and so the semilunar valves open. And blood is forced from the ventricles, oh, wrong pen, from the ventricles into the arteries, because the pressure, remember, was lower than in the ventricles, and obviously blood would then be ejected from the heart. Okay, so we haven't added aortic pressure yet to my graph, okay, but aortic pressure is going to be fairly consistent because of the elastic tissue in the walls. Is going to mean that it can recoil and help to maintain that pressure, okay, but the ventricular pressure is still going to be increasing at this point, and in fact the ventricular pressure then is going to increase far above the aortic pressure. And again, we've got another crossing point here where the ventricular pressure exceeds the aortic pressure, and this point then represents when the semilunar valve in the aorta opens. Okay. Now again, because the semilunar valve has opened, and we've now got the ventricle and the arteries kind of acting as one chamber, there's no barrier between them. The aortic pressure is going to track that of the ventricles because it's now one single chamber, but because the contraction is closer to the ventricular element of that chamber than the artery element, the ventricular pressure is slightly higher. And again, we see then the beginnings of a decrease in both of these because the blood is being ejected from the ventricles and into the arteries. So that's ventricular systole then. Last stage then is diastole. So relaxation of both the ventricles and the atria. The atria have already been relaxed. Okay, so it's just the ventricles that are relaxing at this point. The atria are already relaxed. Okay, so we'll start from where we left off with regards to the artery and the ventricular comparison. So the ventricles have relaxed, increasing their volume and decreasing their pressure below that of the arteries. The arterial pressure now is higher. Oh, I keep going to my wrong pen. And the ventricles. And so the semilunar valves now are going to close, and that's going to prevent blood from flowing backwards. Like that. Okay. And we'll see this on the graph here then, is that the ventricular pressure of ventricles are now relaxing. So the pressure is going to drop dramatically and quickly. Okay. And the aortic pressure then, at this point of that crossover, means that the valve shut, and now the aorta is maintaining its own pressure with its elastic connective tissue, and so actually it stays fairly constant, with a decrease, of course, because the pressure will be lost gradually. So again, we've got a crossing point where the ventricular pressure is now below that of the aortic pressure, and so this represents the semilunar valve closing. And then we've got our final comparison to do during diastole, which is between the ventricles and the atria. So the ventricle pressure then continues to drop as it relaxes further. Now, in the meantime, during ventricular systole, the atria then have gradually increased in their pressure. Now, This is where we want to avoid a misconception here, okay? Because the reason why the ventricles have gradually increased their pressure is because blood has been returning from the veins, from the vena cava, from the pulmonary vein into the atria. And that addition of blood is then going to exert a pressure on the atria, but it's a very gradual increase there, not like the increase we've seen in the contraction of the atria, for instance, and not like the increase we've seen with the contraction of the ventricles. It is a gradual increase there. And that gives us a clue then that it's to do not with contractions of the heart, but actually with the flow of blood into a chamber. Okay, so again, just to repeat them, the ventricles have relaxed, their volume has increased, the pressure is now lower in the ventricles than in the atria, and so the bicuspid valve and tricuspid valve open. Like so, and blood can then actually flow from the veins into the atria and into the ventricles, where they fill up to 70 to 90% of their volume. And we can see that event again, the crossing point where the ventricular pressure goes below that of the atria. And so this is where the bicuspid opens. And then what we see from that point is blood is now flowing from the atria into the ventricles, okay, as one chamber effectively. So their pressures are going to track each other. And after initial decrease, we actually start to see again a gradual increase in those pressures. With the ventricular pressure slightly below that of the atria, because the blood flows into the atria first and then into the ventricles. Okay, so just to add in some timings here then. All right, so atrial systole occurs within the first 0.1 seconds of the cardiac cycle. So this is atrial systole here. I'm just going to track that up. Okay, ventricular systole, then we can see that occurs because the pressure dramatically increases at this point here. Okay, there's a common misconception that this is when ventricular systole starts, when the pressure is already high. But remember, systole is contraction, contraction leads to volume change leads to pressure change, and that then is starting at this point here. Okay, and ventricular systole continues then until we start to see a dramatic decline. So ventricular systole actually takes place right up to 0.4 seconds, halfway through the cardiac cycle. Okay, so that whole section there is ventricular systole. And then diastole begins because the ventricles are relaxed and the atria are also relaxed. So diastole occurs for the remaining 0.4 seconds of the cardiac cycle. And again, we get the common misconception that diastole starts here, okay, where the atrial pressure exceeds the ventricular pressure. But remember that diastole is relaxation, and relaxation then begins as pressure starts to decrease dramatically, okay, not once the pressure is already very low. So that's the key information we need here. There are a couple of bits that people tend to ask about with regards to some of the other slight pressure changes. Okay, one of those is this point here, where you see the atrial pressure increase slightly, okay, during the start of ventricular systole. That occurs because the bicuspid valve, which is facing this way, bulges out as the ventricles increase their pressure. And that actually decreases the volume of the atria slightly as it bulges into the atria. And so the atrial pressure very slightly increases, and then it flips back into its original position and goes back down again at that point. So this is often called the bicuspid bulge, or at that point there. Okay, and I've already talked about why we get a slow, steady increase from the atria there, because of the atria filling with blood from the veins, the vena cava and the pulmonary vein. And then I've also explained why we've got that steady increase during diastole, because the blood is then filling through the atria into the ventricles, and that's exerting a pressure. But that gradual increase, what we must avoid is talking about these increases in pressure during atrial and ventricular systole due to the flow of blood. Remember our sequence, okay? The pressure changes, okay, that we need to be referring to in terms of opening valves is due to the chamber contractions and the volume changes associated with that. Okay, so hopefully that's helpful.